For example 17, the dye dilution method is used to measure cardiac output with 6 milligrams of dye. The dye concentrations in milligrams per liter are modeled by C of t, which is equal to 20 TE to the power of negative 0.6 t, where t is in between 0 and 10 inclusive, where t is measured in seconds. We want to be able to find the cardiac output. So we're going to use definition 3 for the cardiac output, which is equal to the value of A divided by the integral going from 0 to t, C of t dt. Now before we actually solve this, we can go ahead and take a look at the denominator and first find and integrate that function. So we know that t is going to be in between 0 and 10, so our upper and lower limits are 0 and 10. And then we're going to use the function 20 TE to the negative 0.6 t dt. And then what we're going to do here is we're going to integrate by parts. So we can factor out the 20 and then integrate by parts by letting u equal t, and dv is equal to e to the negative 0.6 t. du is equal to 1 dt, and v is going to equal negative 1 over 0.6 e to the negative 0.6 t. So now we're going to use the formula for the integration by parts. So we have uv minus the integral v du. So we have 20 times negative t e to the negative 0.6 t, evaluating it from 0 to 10, minus v du, going from 0 to 10, which is negative 1 over 0.6 e to the negative 0.6 t. So now what we're going to do is we're going to go ahead and then factor out of the integral negative 1 over 0.6. And if we factor that out, it becomes plus 1 over 0.6, 0 to 10 e to the negative 0.6 t dt. And over here, we're going to go ahead and evaluate from 0 to 10. So if we put in 0, we have 0 in the exponent, but 0 is going to be in the front, so we know it's going to eliminate. Plugging in 10, we're going to get negative 10 e to the negative 6. Now the next step here is that we have 20 times the quantity negative 10 e to the negative 6. We factored out that 1 over 0.6. And now we got to take the antiderivative of e to the negative 0.6 t. If we take the antiderivative of that, we get negative 1 over 0.6 e to the negative 0.6 t. And we're going to evaluate that from 0 to 10. But what we're going to do is we're going to factor out this negative 1 over 0.6. If we factor that out, we're going to get now minus 1 over 0.6 squared, since we're multiplying those two. And we have e to the negative 0.6 t going from a lower limit of 0 to an upper limit of 10. And now we're going to go ahead and evaluate that. So we have 20 times negative 10 e to the negative 6 minus, if we square that, we get 1 over 0.36. Evaluating the upper and lower limits, we're going to get e to the negative 6 minus 1, because e to the 0 is 1. Okay, the next step that we want to do is we want to be able to then combine everything to make this a little bit easier for us. So what we can do is we can factor out this 1 over 0.36. When we factor that out, we have 20 times 1 over 0.36. And what we have left here in this first term is negative 6e to the negative 6. What we have left in this term is negative e to the negative 6. And what we have left in this term by distributing that sign is plus 1. So now we can combine these two. So we're going to get negative 7e to the negative 6, and we have 1 in the front here. And now we have 20 over 0.36. Now we can plug this entire thing into the denominator of the cardiac output formula. Now we know that the dye is 6 milligrams. So we know that A is going to equal 6. we know that the integral that we got was 20 over 0.36 times 1 minus 7e to the negative 6. And so what we're going to do is we're going to take this reciprocal of this fraction by now multiplying 0.36 times the numerator, divided by 20 times 1 minus 7e to the negative 6. We take 6, multiply it by 0.36, and divide it by 20, gives us the numerator of 0.108. Divide that by 1 minus 7e to the negative 6, gives us approximately 0.1099 liters per second. Or if we want to write this in minutes, it would be 6.594 liters per minute.